thank you for coming today to the ATAR Notes HSC Physics lecture. Really exciting, this is going to be online, so I'll be reaching even more people this time. So before we begin, just a little bit about me. So my name is Angini, but my friends just call me Jeannie, so you can call me Jeannie as well. I graduated last year in 2019 with an ATAR of 99.8, also state ranked 11th in mathematics. But I kind of like talking about physics more, which is why I'm tutoring and teaching and lecturing physics. But definitely, like in my explanations, I'll be using a lot of maths. I'll be using a lot of the formula sheet and that sort of thing. So right now, what I'm doing is studying computer science as a co-op scholar at the University of New South Wales. So a lot of computer stuff. If anyone wants to talk to me during the Q&A or during the breaks about getting scholarship money and that sort of thing, also really open to talking about that. And just about a little bit about myself, what I do in my spare time, play guitar, cooking, trying to get into cooking because I watch way too much Bon Appetit, and also I've been trying to get into skateboarding as well. So all pretty good things to be getting into during quarantine, actually. Yeah. And so now some housekeeping stuff about how today's lecture is going to work. So today is going to focus on Module 7, the nature of light. Basically, it's just a crash course on the entire module, basically. So it's going to be blocked into 45 minutes. In block 1, I'll be talking about the electromagnetic spectrum and the wave model of light. I'll get to, then we'll have like a little Q&A at the end, and then it'll be a 10-minute break. You can still ask me questions during that 10-minute break. Then we've got another 45 minutes where I'll be talking about the quantum model of light. 45 minutes, then break, 10 minutes, special rel, and then my last block will be about special relativity. So I think the last block will be really important because special relativity is something that you want to learn as many times as you can because it's something that's, I guess, tough to get your head around. Also, just other things. So during the slides, my words will be in red, so keywords that you should be able to define and know what they mean. I do understand that it's a lot of content for 2.5 hours. It's okay not to understand everything now. Learning is repetition. Learning is talking and discussing. So what I'm doing now is just presenting you the entire module so you get an idea of what it's about, so you get like a big picture overview. So then when you go and learn in class, you'll be much better prepared once you actually learn that with your teacher. And also, so the lecture is being recorded, and the recording will be available in the next week or so. Check your emails. So if you missed something, you want to see something again, it'll be emailed to you and you can watch back. Also, I think on your platform, the lecture slides can be downloaded using there's a PDF icon underneath the video. So yeah, you don't even need to copy anything. The slides are there. The slides are there for you to follow along. Also just on a time perspective, I'm not sure I'll actually get through everything through the slides. My idea was I'm going to make slides on the entire module, and then we'll get to cover whatever you guys are most interested in hearing about, and then and the rest that we don't cover can still be a part of your notes. So basically think of these slides as like notes that will help you in your studying. Okay, now this is a weird time also to be doing the HSC, so I'll also be making a little bit of time immediately after your breaks at the start of the content block 2 and content block 3 to talk a little bit about how to study, how to keep your stress in check, and also just tips on how to study effectively in physics. I see a bunch of questions coming in about how to study, the best way to study for a physics exam, and I'll definitely be covering that a little bit. And then also, I see that some people have already got onto this. Get onto the Slido website. Just Google Slido, and then enter the code HPHY. It's like HSC Physics. The password is ATAR. So you can ask me questions basically through the entire through this entire stream, and I believe I'll be setting aside poll times where I'll be like asking you a question for you to vote on which one you think is going to be the right answer. Yeah, so at any time, feel free to just shoot me through some messages. And yeah, and also during the Q&A blocks, that's where you can send messages as well. Okay, all right, let's begin. So the first section that we have is electromagnetic waves. All right. So the cool thing about electromagnetic waves, this being the first thing, is it kind of leads very well off of your last module that you just did, which was electromagnetism. I have a question that's asking me, I have a lot of trouble understanding electromagnetism. What's the easiest way to understand all the laws and all the rules in the topic, and also just the intricacies with that? So I think for that, basically ask questions. The best way is to get the syllabus and mark down what you're confused about, and then ask your teacher, ask your friends, just to ask them to explain that to you. And then as you go through the dot points, hopefully that helps you get like a broader understanding and solidify. But yeah, it's something that takes time that you need to work on. Yeah. So, but if you are comfortable with electromagnetism, we can start with what exactly is an electromagnetic wave. So an electromagnetic wave, it's kind of in the name. It's a wave consisting of electric and magnetic fields oscillating at right angles to each other, which can self-propagate through empty space. All right, that's quite a bit to the definition, so we're going to break that down a little bit. So first of all, about the electric and magnetic fields, you can see that in the diagram. You've got see that the red stands for the magnetic field, and that's oscillating in the horizontal direction, and then your electric field is oscillating in the vertical direction. And then so electromagnetic wave is those two fields oscillating together and self-propagating through empty space. So now that self-propagation thing is very interesting. So let's unpack that. Basically, it breaks down to a bunch of laws. So I think a question I was asking about Maxwell's equations and the laws itself, you don't need to necessarily memorize them, but you have to understand what they mean. So let me know if you can actually see this whiteboard correctly. So self-propagation. It begins with the fact that you've got a point charge, right? So if you recall back in, I think, module 3 or 4 of last year, a point charge has an electric field emanating in all directions. So that's the electric field. Now, when that electric point charge accelerates, that produces a changing electric field, right? So now we've got a, I'm going to draw that smaller. So let's say that that charge is moving up and down. And then so when that happens, it produces a changing electric field, which we're going to draw like this. Now, a changing electric field produces a changing magnetic field, right, at right angles to one another. So I'm going to draw it like, yeah. And then this is due to Ampere's law. You would have learned it again last module. When you have a current moving through there, so this is a wire and a current's going through, it produces a magnetic field. The directions itself right now aren't important, but just the idea that an electric field produces a changing magnetic field. And then what we do also know is that due to Faraday's law, because if we remember Faraday's law, which was the EMF is proportional to the change in flux over time, right? What that tells us is then when we have a changing magnetic field, we produce a changing electric field. So then what happens is that repeats. You've got the point charge producing a changing electric field. That changing electric field produces a changing magnetic field. And that changing magnetic field produces a changing electric field. And then once you have a changing electric field, that produces a changing magnetic field. And then the cycle repeats. So that's what we mean by a self-propagation. The EM wave kind of, once it gets going, it creates itself. One component of it is creating the other component. And this happens across the electromagnetic spectrum, so we can have waves of different frequencies. Okay, and now these electromagnetic waves, I think the syllabus asks you to understand that they were predicted by James Clerk Maxwell. So the syllabus is actually quite specific about what they want you to know from Maxwell. They want you to know that he was the one who put together the 4 equations to unify electricity and magnetism for the first time. So what he did was he took together 4 equations. So that was, I was mentioning before, Gauss's law, Ampere's law, Faraday's law. You don't actually need to know what the laws are, but you have to know that what they did was they brought together electricity and magnetism and saw that they were kind of produced each other and sort of like were very closely linked. So yeah, again, Maxwell's equations specifically, so their specific equations, what they are, is beyond the scope of the syllabus. But we do need to understand what they mean. And so what they mean is that electricity and magnetism are unified. And also it would result in these electromagnetic waves, which we define again as self-propagating waves with electric and magnetic fields oscillating at right angles to one another. So before, people actually didn't know, people have never seen electromagnetic waves. People didn't know what electromagnetic waves were, but what Maxwell did was when he put those equations together, he said, okay, there must be these waves that exist, and he described their behavior. By also rearranging the equations, he was also able to predict the speed of those electromagnetic waves. So again, this equation, so that's those are 2 constants that he used in those equations. You don't have to memorize this formula, but you do have to know that he predicted the speed of electromagnetic waves to be 3 times 10 to the 8 meters per second. This figure should be familiar to you. That is the speed of light. So at this point, Maxwell was like, is that a coincidence? He started to suspect that light would be a form of electromagnetic wave. And we'll be exploring that idea a little bit further later. But yeah, okay. So now we've come to our first question. This is just an example that I'll be walking through, but feel free to have a go at answering. So this was from last year's HSC. I think it's like the most standard question that we got last year, actually. So it's got, the diagram shows a model of electromagnetic waves. There you go. Relate this model to predictions made by Maxwell. So I think this question is really good because it gets to tie together just what we talked about just then. And I'll also, as I talk about this, I'll also break down how I approach answering short answer questions, and hopefully that is helpful for you guys too. Yeah, so for these short answer questions, when you are in the 3 to 4 mark range, you'll get a lot that are like specifically to one single module. I think someone just asked will the more longer response questions be derived from a specific module? No. The longer questions definitely, from last year especially, they seem to pull together a lot of modules. Yeah, but okay, let's go through how I would answer this question. So, actually, let's see if I can get into editing mode. Oops. Let me get back to where I was. Okay. All right, so the first thing that we see is that we can notice a couple things first off. So one, it's 4 marks. 2, it asks, relate this model to predictions made by Maxwell. So what do we need to know? We need to know the predictions made by Maxwell. So we need to state those, and then we need to relate how that relates, relate that to what in the diagram we see before us. And also, if we look at the fact that it's 4 marks, so we've got a statement and a link. So that seems like a 2-marker response. So it's asking for 4 marks. So that kind of tells us we'd probably need 2 examples. 1 example probably isn't quite enough. 3 examples seem like overkill. But that being said, if you do 3, they're not going to take marks away. But yeah, so what were some predictions made by Maxwell? So Maxwell predicted that an electromagnetic wave would consist of a electric field oscillating perpendicular to a magnetic field. So let's write that down. Right, so that's our first step. I'm like, okay, we know a prediction. And then let's link that to how that's shown in this model. So we can see that in this model, it shows, see that electric field is going vertically, and that magnetic field, denoted by the B, is oscillating horizontally, right? So so I can just state like this is shown in the syllabus. This is shown in the model. Field in the vertical direction is perpendicular to the field in the horizontal direction. And I'm probably being a little bit overly wordy. You could definitely get away with being a little bit more brief. Honestly, even in the thing with physics is like they don't really care about coherency. You could literally write this as dot points. You'd be like prediction, and then this is shown, and then the model shows this. He also let's also notice in the model we've got that oscillating charge, and we should recall that what Maxwell did was he predicted that electromagnetic waves would be produced by oscillating charges. So Maxwell predicted that EM, let me just say, EM waves are produced by an oscillating charge. This can be seen in the model. Where the source of the electromagnetic. It's okay to use abbreviations as long as you like show the marker what they are. Is oscillating charge. All right, and there you go. You've answered the question. You could also have talked about that the fact that the electric and magnetic fields are perpendicular to the propagation direction. That's also something you could talk about. Yeah, that's something else that's seen in the model. Okay, I had a good question. There's a change in electric fields, but how is there a change in flux? Okay, all right. So if you recall transformers, right? When you have a changing electric field, that produces a changing current, changing magnetic field. Because that magnetic field won't be the same amount all the time because the strength of that electric field is changing. So since Faraday's law is that the changing current is proportional to the change in flux, when you have that electric field is changing at a different rate. So like when it's smaller, the magnetic field is also smaller. When the electric field is bigger, the magnetic field is also bigger. So that's why when you have a fluctuating electric field, you also have that fluctuating flux. Like that flux is also changing. Yep. Okay. So I'm going to leave that on the slide. And then so then the next point in your topic is about measuring the speed of light. I'm not going to spend too much time on this because it's you can just read about it, you can memorize. There's not much to understand. The key takeaway is the fact that scientists are always trying to improve and refine their methods of measuring stuff. So over the years, scientists have tried to measure the speed of light, starting from Galileo in the 1600s to like better methods now in the 1900s. I don't know if they still do it in 2000s. We kind of like settled on the speed of light. We've like actually like defined speed of light rather than measuring it. But yeah, while they were measuring it, they kind of got really close to Maxwell's 3 times 10 to the 8 meters per second. Yeah, so your key takeaway is just like scientists are always trying to improve and refining and coming up with I think new ways of improving on what they've done before. It would be useful if you have time to understand. So this is just like base Googling, understand what they did, getting the data that they used, and then calculating the speed of light for yourself. They all kind of come down to the fact that speed equals distance over time. They just like measure the distance that light has traveled and then try to time how long it took for light to travel. Yep. So that. Oh, okay. And then what stops the cycle that causes an electromagnetic field repeating in a normal circuit? It doesn't stop. It doesn't stop at all. That's why it's self-propagating. It goes on forever. Yeah. So like once an electromagnetic wave is like created, I guess, like it goes on forever. Like it bounces around and that sort of thing. Yep. Okay. Now we will. Oh, I should be ticking. Sorry. I'm figuring out how Slido works. Yeah, so like the flux, someone asked the flux requires a loop or coil, whereas it is in a vacuum. Flux doesn't actually require a loop or a coil. It requires in order to like be observed and like used, yes, it does need to be in a coil to produce a current that actually goes somewhere. But when it is not in a flux, like there is actually still produced an electric field. It's just not directed. It's just like sort of floating in air. I should start ticking the questions that I have answered. Okay, so there's a lot of questions on Slido that I'll come back to maybe during like the Q&A/breaks, because they're a bit more general about how to study. Are there any practicals associated with this model? I'll get to them as we get to it. What are some obvious mistakes to avoid when writing HSC answers? So like the obvious mistake would be not defining things. Or like not addressing parts of the question. So like when it's asking relate this model to predictions made by Maxwell, like your number one thing is like to talk about a prediction made by Maxwell, and then talk about something specific to the model. I think a common mistake is just kind of regurgitating what you know and then not actually addressing what's on the page before you. So if you just talked about Maxwell's predictions and then like drew your own thing, that would be a common mistake. And then someone said, how does an accelerating point charge cause a changing electric field? Okay, so if we've got a point charge here, and it's got a field like this, once it like moves down, so it's like here, right? Let's pretend I've got the thing and then it like moves up. Right? You can think of it as like the point, you can think of this, the electric field like wave following the point of, I guess, like maximum electric field. So here, like that's the point of maximum. So then as it like comes down, it like the point of maximum electric field goes down as well. So then if we do that over time, that comes up with a wave. That is a terrible diagram. But like the point is that it just like, because your charge is moving up and down, that point of like maximum electric, that point of like where the field is goes up and down as well. Yeah, so that's how an accelerating. You think of like a, yeah, so like if the point charge that's producing the electric field is moving, then that like electric field is also like moving. Oh, good question. Why can a self-propagating electromagnetic wave not go through everything? And why do different waves go through a different amount of things? That's a really great question. It's to do with, electromagnetic waves do get blocked by stuff, and it depends on their frequency. So their frequency is like, it depends on their frequency. If their frequency is small enough, it will get through stuff because, waves will be blocked by particles. And then so when you've got a small enough frequency, it won't be blocked by that. If the particles are like far enough apart, it'll like go through. Whereas if the particles are like super tight together, even if it's like, and it's got like a larger frequency, it's not going to get through. We'll talk about wave behavior a little bit more as we talk about the wave model of light. How am I doing for time? I've got about 20 minutes to go. Okay, so wave model of light. As I said, this module is kind of all about light, and we're going to talk about. There's been this battle since like the 1600s on what light is. So Isaac Newton, your old friend, you would have learned about him with all the gravity stuff. He thought that light was a particle and he called it a corpuscle. Versus there was another guy called Huygens who believed that light was a wave, right? And then so we're going to talk a little bit about, in this topic, we're going to talk about the evidence that shows that light is a wave. So people observed that light could reflect, refract, and diffract. And both those, all three of those behaviors could be explained by both the particle model and the wave model. But the thing is, other behaviors like polarization and interference, which we observe light to be doing, could only be explained if we thought of light as a wave. So we're going to go through polarization and interference and show how the behavior of light as it gets polarized and as it interferes with each other, how that shows that light must be a wave. So yeah, first polarization. I'm going to rub all this stuff out. So polarization means of a light wave refers to the direction of oscillation of its electric field. So we're under the assumption that light is an electromagnetic wave. So normally light is unpolarized. It is in all directions. So if we go back to this diagram of an electromagnetic wave, as you can see, that electric field is going in just like one direction. It's like vertical. But in reality, light exists as like lots and lots of electromagnetic waves. And then so they might be at different angles. Like it'll still all be perpendicular to its own magnetic field, and it'll still be perpendicular to the propagation direction. But like, so if we pretend that we're front on, if we're viewing this field coming front on, the direction of the, so for this one, this would be the direction of E field. But there might also be another electromagnetic wave, which is oscillating in that direction as it's coming towards me. So EM waves traveling out of the board. And there might be another one which is oscillating in that direction and in that direction. So yeah, normally light is unpolarized, but we can pass it through a polarizing filter, sometimes called a polarizer, and once it comes out of it, we call the waves plane polarized. So what a polarizing filter does is it cuts out all of the waves that aren't oscillating in the right direction. So in this example here, the polarizing filter is in the vertical direction, right? So then here we've got unpolarized light coming in here, and then once it hits here, it cuts out all the horizontal parts. It cuts out all the horizontal components of these electric fields. So this one disappears entirely. This one becomes a bit smaller because the horizontal component disappears, and then you've only got left with the vertical component. So once you've got once you see light that comes out of the polarizing filter, it's only in a single direction. It's only in that vertical direction. And we call this polarized. Once it's been polarized once, it would call it plane polarized. And then this is a link. I'm not sure we have time right now, but it shows. Actually, let's follow the link. Let's go through it a little bit. Yep. So you've got that unpolarized light, and then it goes through this one, and then it all collapses into a single direction. And then we're just going to show one slit, and then so yeah, since it's already in the vertical direction, it just goes straight through. But then as you rotate that polarizer, the direction of the wave leaving it changes as well. And when it's at 90 degrees, it's gone completely. Yep. Yeah. And then so one key thing to note is that when unpolarized light gets polarized for the first time, the intensity of the light will halve, right? And that's because when it's in all directions, so say you've got a vertical polarizer, it's in all directions. It's the light has like half of the components will be in the horizontal direction, and half of the components will be in the vertical direction. So generally, yeah, once it goes through the polarizer, it cuts out half. It cuts out everything that was in the perpendicular direction. So then your intensity is half of the original intensity. And then, so coming back to the prac thing, this usually would be a prac where you would, so like something like this, where you would get like two polarizing filters and rotate them and look at the way that the light intensity changes as you look through maybe like the sun at different angles or at reflected light at different angles. You can do this at home if you have a pair of polarized sunglasses. Polarized sunglasses are its own polarizing filters. That's how they work because they're polarized in one direction, right? So all the light that you see gets halved. Yeah. Yeah, that's so it like cuts out the light that's like reaching your eyes. So this is like a more generalized version. So the polarization of already plane polarized light. This is Malice's law. So this one's pretty important to. It's on your formula sheet. It's important to use because you will get some calculation questions on it. And then so I is the angle of the I is the intensity of light as it comes out of the polarizer. I0 is the intensity of light as it comes in, like of the plane polarized light coming in. And then theta is the angle between the polarization direction of the filter and the direction of the incident light. So in this example, we have, so sometimes we call the second polarizer an analyzer. And then so we've set this at 45 degrees. So I'm going to show you an example of how we calculate that. So here so let's make that I. So let's say incident light is 10 lux. Right. Intensity 10 lux. And then we want to figure out intensity afterwards. Alright, so then I equals I0 cos squared theta. So we sub that in, that's 10. And then cos squared 45 degrees. So if you remember your exact ratios, cos 45 degrees is 1 over root 2. So then when that's squared, we get 10. Our intensity has been halved. And then we get 5 lux. So that would be the intensity of light as it comes out of this particular analyzer. So basically, then that tells us that whenever the analyzer is at a 45-degree angle to the direction of the already polarized light, the light going through will halve as well. Okay, so let's start a Slido question. I'm going to have a go. So I'm going to leave this question up and I'm going to run a poll. I'm going to create a poll. So let me know if you guys can see it. So basically the question is, unpolarized light is passed through a polarizer so that it is now plane polarized in the vertical direction. So we have plane polarized light. As it leaves, it passes through a second polarizing filter. At what angle should the direction of polarization in the second filter be so that no light passes out? Okay, we're starting to get responses. Good. So just to help you visualize, so basically we've got the question is asking you, so if you've got light coming here, what does this angle need to be so that no light comes out at all? I'm going to leave a little bit of time to do that. Let me know if you're having trouble finding the poll. Okay, so someone asked, are we only polarizing the E field? The way that you think about it is that you're polarizing the E field. Once the E field gets polarized, if the E field is cut out, like the B field is cut out along with it. But like for our purposes, it's easier to only ever think about the direction of the electric field. So everything is like the polarization in terms of the direction of the electric field. Someone asked, does temperature affect the motion of light? Great question. I've never thought about that before. I don't think so. I don't know how it would. Because there's no, it's a wave. There's no like yeah. I don't think it does, but take that with a grain of salt. Yeah, and then someone asked, what is the best way to define wave particle duality? We'll get to it in Module 8. Don't worry about it now. And I'll talk a little bit about it at the end. But yeah, don't worry about that right now. Does the amount of movement from the point charge affect the frequency wavelength of the EM wave? Great question. Yeah, it does. It does. So if that point charge is moving a lot, then yeah, obviously your amplitude's going to be a bit greater. If it's moving faster, your frequency is going to be a bit greater because those like peaks and troughs are happening more quickly. Yeah, but I think for the purposes of this module, we don't focus too much on the point charge part of it. We mostly talk about what happens to the EM, how it behaves once it is an EM wave. Okay. Oh my gosh, we have 193 responses. Okay, I'm gonna put an end to that now. The answer is 90 degrees. I'm gonna rub this out. Yeah. So what happens is that, so this is like the plane polarized light. And if we were to place an analyzer at 90 degrees, so let's say that's the direction of analyzer. What that analyzer does is it's only letting light that was in the electric field in the horizontal direction through. So then in this one, there's nothing in the horizontal direction, so nothing gets through. So that's why when it's perpendicular, no light comes through. Also, if you were to do it mathematically and you just like subbed into the formula, you would be looking for when cos squared theta would give you 0. And then if you do inverse cos, you find that theta equals 90 degrees. Okay, cool. All right, now let's move on to the double slit experiment. So we're going to look at light interference. So a quick recap on how waves behave. So I think someone was asking about whether how much year 11 content you need to know. So you need to know how waves work. You need to know that waves diffract, and you need to know about wave interference. So when waves are in phase, their troughs line up with each other, their peaks line up with each other, and then so that's constructive interference, and you get like that stronger, like higher amplitude wave, versus when they're out of phase, when they're like off by half a wavelength, their peak lines up with their trough, so then they cancel out, and they've got destructive interference. So then let's talk about how this is important. So, so what they did was they did an experiment which showed that light could behave like a wave in the sense that it would diffract and interfere. So what they did was they set up the double slit experiment. This is something that you would do as a prac. Actually, it depends on the school. Like it's a bit fiddly, but you can, if you like buy a double slit off of eBay, you can actually do this at home. So you've got two slits that are really close together, like a millimeter close together, and you've got a screen really far away. And then what happens is you send through a single source of like light through where it gets to the slits, and then once it like gets through the slits, what happens is each slit becomes a point source. So now we have two identical sources of light. And then so once they get out, what happens is the light waves will diffract, and then the light from the two sources will interfere with one another so as you can see here, the light waves from one of these sources meets the light waves from this source, and that produces an interference pattern of dark and bright spots on the opposite screen. So before we go ahead, because the point of this is to show that light is a wave, so what would we have expected from this experiment if light was a particle, or if light behaved as a particle? So I'm just going to draw a quick diagram of this here. So that's like the two slits and that's the screen. So if we thought of light as a particle, so if we're sending in light, we're sending a lot of light particles basically, right? So if light was a particle, we'd see these particles coming in through like this. Like so some light would be blocked, and then you would end up with like two bright spots directly opposite. But this isn't what happened. Instead, we found that interference pattern. Instead, we found the interference pattern. So we had like a central bright spot in the middle, and then like dark bands, and then bright bands, and then dark bands and bright bands. Okay. Just warning you, I think I'm probably gonna go 5 minutes over time into this break. That's okay. I'm still gonna give you guys a break though. We'll just have to cut stuff from later. So the interference pattern on the screen is actually caused by the fact that the light from each point, so the light from this source here and the light from the bottom source, they're traveling different distances to the point on the screen. Well, in this case, so in the central point, where it's the point of the brightest, light is brightest, at this point they're traveling the same distance. So when that happens, the light waves that reach that point, they actually match up like this. Oops. Like this, right? So what happens there is they constructively interfere, and then so when they constructively interfere, that point where they meet, that point is bright. And this also happens when so the important thing is looking at the path difference. So on this diagram here, you can see that this is the distance traveled by light source 1, light from source 1. This is the distance traveled by the light from source 2. And then so if you draw like a perpendicular line there, you can actually see that this, the light from the second source has traveled an extra 5.01, they don't have units here, I'm just going to say millimeters, 5.01 millimeters, to traveled a longer distance of 5.01 millimeters. But the thing, actually, it'd be better to say nanometers, I think. 5.01 nanometers. But as you can see, you've got a wavelength of also that's 5. So then that means they're perfectly still in phase. The peaks are still going to line up with the peaks as it reaches this spot here. So at this point, we still have constructive interference. But what happens at the dark spots on the pattern? That's where they're out of phase. They're perfectly out of phase. So here, the extra distance that this the second source of light has traveled is half of a wavelength. So that means it's half a wavelength out of phase. Or it's like half a wavelength off. So when it's half a wavelength off, instead of being here, instead the wavelength will be like down here. It'd be at one of its troughs. Hang on, I didn't draw that right. Like that. Yeah. I didn't draw that. Lower. Right? So then they destructively interfere. Okay. So we actually have a formula for predicting where the bright spot is. So I think I said there would be a break at this point. Stay just for this part where I look through the formulas, and then I'm going to just run through a example. So then that's like, if you want to stay for that, sure, or you're allowed to, but yeah, stay for at least like the next like 2 slides. Okay, so we can actually predict the location of the maxima of the bright spots and the dark spot using the idea that that they interfere, that the interference is constructive when the path difference is equal to 1 wavelength, or like a whole number of wavelengths. So let's draw this. So that formula is d sine theta equals m lambda. So I'm just going to show what that means. So in this setup here, d is the distance between the 2 slits. Right? And then, so then theta is the angle from the center line to the point of the bright spot. So let's say we have a bright spot here. Theta is the angle between the center line and that. And then m is the order of the maxima. So m equals 1. So that's the first bright spot that occurs after the center line. So we'd also have one same distance away here, which is also m equals 1. And then we'd have another one, maybe like up here, where m would equal 2. And then there's a corresponding one down here where m is equal to 2 as well. Right? Yeah, so those are the bright spots. And wavelength is like the wavelength of the light that's coming in. And then the dark spots, on the other hand, so they would occur here. They would occur in between. So again, like the same deal, m, like d, theta, and m mean like the same thing. So m equals 1 for the first dark spot, m equals 2 for the second dark spot, and then the same on the other side. Right? But then because a dark spot occurs when you're off by half a wavelength, your formula is going to be m plus half times lambda. I think a bunch of people have gotten onto that question. I should probably address this question actually. Yeah, so in this question, a monochromatic light of wavelength strikes a double slit and produces bright and dark fringes on a screen. So that's the double slit experiment. Light from slit S1 travels along path 1, and light from slit 2 travels along path 2 to produce the dark fringe shown. And then what is the difference in length between P1 and P2? Okay, so I'm looking at this and I've noticed that a lot of people have answered with lambda on 2, and that's understandable because I seem to have I talked about the fact that when you're off by half a wavelength, that's where the dark spot is. So, but the thing is, you got to be super careful, is because off by half a wavelength also depends on like how far off you are. So it depends on the order of the dark spot. So on this diagram, we see that this is that point is actually, so if we go off of like the central bright spot, we've got dark spot 1, and then this is we're actually looking at dark spot 2, right? So here, m would equal 2. Right, so then if we sub that into this formula, what you would end up getting is that, so if we're looking at the path difference, it would be, so the path difference here is lambda on 2, so it's half lambda. But here, it's actually going to be 3 on 2 lambda, because you've increased it because it's like a bit further away as well. So at the first one, you'd be off by half wavelength, and then the second one, it's the next cycle, so you're off by 1 plus half a wavelength. So same with the bright spots. So over here, you'd be off by 0. But then over here, where m equals 1 for the bright spot, you'd be off by 1 wavelength. And then over here, where you'd be off by 2 wavelengths. That makes sense. I'm actually gonna, I think that is a good time for a break now. So yeah, just quickly, the pattern can be improved by using a diffraction grating, where it's basically just got more slits. So instead of 2, you're gonna have like, I don't know, like 10, 1,000, 100,000, I think they have. Yep. But that's, I guess, like a minor point in the syllabus. Yeah, so right now we're just gonna go for a quick 5-minute break, where you can ask questions, and I'll spend some time answering them. How can electromagnetic waves be created? Doesn't that disobey the laws of conservation? Really good point. And it was a point that I tried to figure out last year as well. Oh man, did I end up figuring it out? I think because, I'll get back to you on that one. I'll think about it. I think I can answer questions on like the ATAR Notes forum later. That's a really good question. I'm going to say that because the magnetic field is also inducing an electric field in the opposite direction, maybe, that it sort of like ends up cancelling out. Like, you know how with back EMF, like you're producing with back EMF, you're producing uh, the magnetic field, but then it just ends up producing you're producing the current, and then which ends up producing a current that goes backwards, which ends up canceling it out. Someone asked. Okay, so big question. I'm having a lot of trouble understanding electromagnetism. Oh, I answered this at the start. What's the best way to study for a physics exam? I will come to that. How many past papers did I do before my HSC plus trials? Well, I had the privilege of being the first cohort doing the new syllabus, so I never actually had any past papers to do. But what I did do was you kind of have to be, so like I can't tell you like how many past papers I did because I never did any past papers. What I did instead was go through past papers and find the relevant questions to me. And also also I think NESA published like a bunch of like sample questions, so I did all that. I found textbook questions, I was doing those as well. I think all up okay, well, what I did, part of my study strategy was to have a single document with like every single mistake I ever made while I was practicing these questions. I think that document is about 8 pages long, last I remembered. So I so I was just like making a lot of mistakes, so like I was doing like quite a bit of practice. So yeah, I don't think there's like a number. A lot of people ask that, like how many practice papers did you do? Just do as much as you can to feel confident in how you're going. How much of the year 11 course is expected to be in the exam? Nothing in the year 11 course will be tested specifically, but it's like assumed knowledge. So the way that I talked about electromagnetic waves, it kind of assumes that you know how that like a point charge has an electric field. When I was talking about the double slit diffraction, it assumes that you know how light waves work. It assumes that you know that waves can diffract and interfere when they're like out of phase or in phase. So you're not going to get a specific year 11 question, but you're kind of just expected to know it. That being said, the one thing that doesn't come up is thermodynamics. I've never applied that anywhere. I just have never had any use for thermodynamics. And like it's not particularly relevant to that course. So like if you don't understand thermodynamics, I think that's the one part you could be like, okay, no stress. But other stuff like waves, electricity, magnetism, definitely need to know. Someone asked, how well does physics scale? Well, but also you need to do well. How do you study and memorize pracs done in class? Okay, that's a really good question. I think first step when you're doing those pracs in class, take good notes on what you're doing, and then once you take notes, that means once you get back to it, you kind of have an idea of what's going on. I really recommend writing methods. When you rewrite the method for a prac that you've done in class, that really makes sure that like you understand what you're doing, why, what you're measuring, and why. So yeah, that's how I had a list of pracs that I'd done, descriptions of the pracs, and all I did was so like part of my study was just looking through them. I was like writing a new method for it, and then sort of like explaining the theory behind it. What really helps is like trying to like teach it to someone. So yeah, my mum heard a lot about physics last year. What are the best ways to understand a topic to the fullest? Like, how do I know if I understand it enough to answer a question about an exam? If you're able to teach it to someone. If you got like, I don't know, if you have friends in year 11, or if you have one of your friends who doesn't do physics, if you're able to explain it to them and they're like, oh, okay, That's how you know you understand a topic well enough. Do EM waves interact with each other? Yes, they'll like interfere. So as we talked about, like the interference, um, they can, yeah, collapse and that sort of thing. They don't really affect one another though. Uh, yeah. Um, I think definitely in the Year 12 syllabus we deal with it in a very simplified way. Um, so yeah, you don't have to worry about them interacting with one another beyond double slit experiment. Um, will we be going over module 6? Sorry, we don't really have time for like to go over everything, but we do have like a trial revision lecture later in the year, and I'll definitely take a note to like go over a lot of module 6 stuff because that seems to be a big pain point for everyone. What do we say when they ask for a prac if our prac at school didn't work? For us, physics experiment never work, or 99.99% inaccurate? Great question. You talk about it theoretically then. You talk about it in terms of what they're meant to do. Because the thing is, like, when you do it at school, there's so many variables that are, like, uncontrolled. Like, your equipment is, like, half broken and kind of old. And then, like, I mean, to be fair, like, we're not the best at, like, taking measurements accurately. So, yeah, it's just kind of down to you describe what happens theoretically. Someone asked, what's the purpose of polarizing light? So one would be with sunglasses. If you want to cut out a bunch of light because you don't want to see all of the light, you want to lower the light intensity reaching your eyes. When you polarize light, it reduces the intensity. Can I redefine diffraction? Diffraction is when light passing through light passing an object bends around an obstacle, basically. Will we have to derive the original formula to find the equation we use in the question equation during the exam? Malice's law wouldn't have to derive. The double slit experiment, the d sine theta thing, no. I'm gonna say tentative no, but I will say understand it. There's definitely videos up online on like Khan Academy and stuff that do explain it. Yeah. Okay. I think, yeah, so I kind of like answered questions throughout the break. But yeah, let's get started again. All right, so first, part of the Tute Smart thing, part of ATAR Notes is that we want to bring free lectures to everyone to teach everyone about physics. But we also have like something classes that happen every single week. If you kind of want to have a bit more like personalized experience and a more consistent stuff. So a lot of the content here, I'm sort of like breezing through. I'm like, okay, we're just getting a big picture overview. In classes, we get to actually talk about it in much more detail, and I'll do stuff like deriving things. Yeah, and so Choose Smart classes are really cool because now they're fully online. So they're kind of like this, where you're able to interact with your tutor while we teach, and every single week you'll turn up to class, we'll explain a topic, you'll get questions at the end of it, and lots of cool resources. So what I'm going to do is up on my screen here, what you've got is the dashboard for if you're a student taking Tute Smart classes. So you can enroll in multiple classes. So as you can see, this person's enrolled in Chem, English, Bio, wow, 4-unit maths. Unfortunately not physics. You can see upcoming live stream classes. So every single week we'll live stream a class just like this. Usually your tutor will be creating resources like worksheets. You can book 30-minute private tutoring sessions. You can look at your class progress. So obviously this person hasn't watched all their lessons. But what you can do is, I think bio is pretty cool. So you can click on bio and you can see, so for up here is the curriculum, what they teach every single, like it's all planned out. We plan it all out for you guys at the start of the year on what every week is going to cover. And so this is like where the live stream happens. There's a live video chat for you to communicate with us, announcements, resources. So if I look at a different week, yeah, so there's like slides and worksheets. You can ask questions and all of that. Yeah. So yeah, that's really awesome. That's what I get to do every single week. So if you're interested in that, we have a little promo happening. Yeah, so we have a special promo for this lecture series. If you want to try it out, enroll in a bunch of classes, see if you like it. You get 7 days free when you use the code TSOnline7. So yeah, so sign up in an account, enroll in a couple classes, and then add that code in, and you'll get 7 days free. Okay, let's get into it. So before we start, just now, I want to talk a little bit about tips for studying and stress, because I see a lot of questions coming in. So I probably do have to address the fact that you are now studying from home for like the near future. It's actually a pretty good thing. You don't have to commute. I used to commute like an hour to school every day. That was annoying. You don't have as many commitments. If you were doing sport, if you were a prefect, you've suddenly got way less to do now. So you got more freedom to study when you want, how you want. But that's also a double-edged sword. Now you've got a bit more time to procrastinate as well. So there's lots of tips out there. I could talk on forever. Like you can read blogs about how to study. We literally had a Smash HSC like a study skills lecture this week, which will like have lots of tips. But at the end of the day, the most important thing is to figure out what works for you. Because what works for you is going to be different to like what works for me or for your friends, and that sort of thing. And I guess a lot of people talk about, oh, like how do I haven't figured out. I seem to study a lot, but it like never seems to go anywhere. Well, or like I'm not motivated. Well, part of it is that you need to keep trying like new strategies to figure out what works for you. So I'm just gonna let you know what worked for me. Last year, I used to be a big procrastinator in year 10. Like every single assignment was like the night before, all-nighters. But in year 12, it was a work in progress. I tried lots of new things to help me study. One thing that worked for me, obviously you can't really do this now, but I used to study on the train because you've got no internet, you've got no distractions. Get on a train after school, bang out an essay or like do a practice paper, look up, you're in Hornsby, but your essay's done, and then you just come home, you get another essay done, something like that. That worked really well for me. I used to do loads of to-do lists because I'm a very forgetful person, so I just needed to write everything down, and that sort of organized my thoughts. So I'd see, okay, this is what needs to get done. There's like, I think people more professional at this than me like do like bullet journaling. I think that's pretty helpful too. And then the Pomodoro timer, which is like, it's this app where you like hit a timer, you study for 25 minutes, and after 25 minutes it'll tell you it's a break time. Take a break for 5 minutes, and then after 5 minutes you go back to studying. That really helped too. Yeah, and also just about taking care of yourself during year 12. Year 12 stress is unlike stress that you'll feel in any other time. It is okay to not feel okay. And I think when you're feeling not so great, it's important to know that like taking a break sometimes is like what you need to do. And I think when you take a break, you can pause, you can reflect, you can think about how am I feeling, what is making me feel this way, and then what can I do about it. And then based on what you want to do about it, then you can think of, oh, do I just want to take the rest of the day off, or do I want to talk to someone? I think also talking to someone is really good. Keep up with your friends on like Zoom. Talk to your family. Your family's like at home now all the time. Talk to teachers if there's teachers that you like. And also, but also if I'm listing off these people, you're like, I don't really want to talk to any of them. There's also there's services just for that when you don't want to actually talk to anyone that you already know. So Headspace is a cool thing. I think they have like a messenger app where you can just like talk to a mental health professional anonymously. You can talk about what's stressing you out, and they'll help you out there. There's a lot of questions about how much do I study. That will be addressed in the second after the second break. Yeah. Okay. Yeah. I'll probably stay at the end. Oh my god, there's so many questions. I'll get to the end and then I'll try to prioritize answer as many questions as I can. But yeah, now we got to get started on the quantum model. All right. So with the quantum model of light, this was like an alternate thing that got developed as we found out that the wave model of light, which did explain like stuff like diffraction, interference and polarization, scientists started to see things where the wave model of light couldn't explain things. So this was the ultraviolet catastrophe and the photoelectric effect. So we're going to go through those and then how that helped us develop, I guess, our quantum model of light. Because these were situations where the photon model could explain it, where the wave model couldn't. So the first thing that we're going to cover is the ultraviolet catastrophe. So as an intro to that, we talk about this thing called a black body. So a black body is this theoretical thing that that's a perfect absorber and emitter of electromagnetic radiation. So what it does is like a good approximation of this is a star. So what it does is it doesn't reflect any radiation. It absorbs the radiation that comes to it and then re-emits all of it. And then black bodies will emit radiation across the electromagnetic spectrum, which we graph these as a black body radiation curve. So this is what it looks like. So what we've got is wavelength down the bottom. So across. So because it's emitting across the electromagnetic spectrum, that means it's emitting at different wavelengths. And then on the y-axis we have the intensity, so how much light is being, or how much radiation is being emitted at that particular wavelength. So on this, we have a couple of different curves. So the radiation that it emits is completely dependent on temperature. So let's look at this curve produced by an object at 6,000 kelvins. So as you can see, so like at this particular wavelength, it's producing it's emitting the most amount of light. And then as you go up to radiation of longer wavelengths, it's emitting a little less of that type of radiation. Okay, So scientists tried to, so this was found experimentally. They had a whole bunch of experiments where they heated up things up to like 3,000 kelvins, 4,000 kelvins, 5,000 kelvins, 6,000 kelvins, and then graphed and then measured how much radiation was being emitted at each wavelength, and then produced these graphs. So that was great. We had the experimental curves, and then scientists tried to use the wave model of light to predict the blackbody radiation curve. So they came up with, so for 5,000 kelvins, this is what the experimental measurement was. And by using the classical theory, when they rearranged the equations, they got this. So, hope you can see, what's the problem with their prediction? Problem number one, the classical theory does not match the observed curve. That is nowhere near close. Problem two, as you can see with this curve goes up to infinity. So that would suggest that at like your lowest wavelength, you would be emitting an infinite amount of that radiation. This violates conservation of energy. We cannot have infinite energy. This curve is not only wrong, it's physically impossible. Okay, so then this failure became known as the ultraviolet catastrophe. Because imagine being a scientist, I think 1800s, early 1900s. Imagine being a scientist then. We know that light is a wave, but if we assume that light is a wave, we can't calculate blackbody radiation. So a guy called Max Planck came up with a mathematical trick to fix it. So so this was the beginnings of the quantum model of light. So he considered radiation to be emitted in discrete packets called quanta. And he said that the energy of each quanta was attached to frequency. So basically the energy in that quanta, it had the frequency and then times h, which is Planck's constant. So then this allowed him to formulate a new law for the curves, which unfortunately we don't learn. Also, we're going to come back to, once you start learning module 8, you'll definitely revisit this idea, the fact that the energy of a quanta is attached to is dependent on its frequency. But what we do learn is Wien's law, which is also kind of based on this idea that we can predict radiation based on temperature. So what this formula is wavelength, maximum wavelength is equal to a constant on temperature. So as you can see, we see that, so what this quantity is the wavelength of the radiation of peak intensity. So that's the wavelength where it's emitting the most radiation. And what this formula is saying is that this is going to be entirely dependent on the temperature of the object, not anything else, like not how large it is, not how small it is. It's based on its temperature. So as you can see with this wavelength, at this temperature, so at 3,500 kelvins, it's emitting the most radiation at this particular wavelength, versus this object at 2,500 kelvins. It's emitting the most radiation of this particular wavelength, of a slightly longer wavelength. Okay, so I'm going to go through a quick example of how we find the characteristic wavelength of our sun. Hang on a second. Hang on, I think I've stuffed up my poll. Okay, so, alright, yeah. I was just fixing something up with the poll. Alright, so what we want to do is finding the characteristic wavelength. So that's the wavelength at which it emits the most radiation. So our sun has a temperature of 5505 degrees Celsius. But then it's important to note that this formula, the temperature is in kelvins. So let's first convert that to kelvins. So add 273, which gives you 778 kelvins. So then we sub that in, we find that max is equal to, so B is 2.898 times 10 to the negative 3 meters Kelvin over 5778 Kelvin. Right, and let me just calculate that. You can calculate this yourself. That gives you about 5.0156 times 10 to the times 10 to the negative 7 meters. That's what 5. Let's write that 5.02. Right, so that's the wavelength at which our sun emits the most energy. So we've got this question. What is the best? So pull up your Slido. We've got this question. The graph shows the electromagnetic radiation emitted from a black body cavity. What is the best estimate of the temperature of this black body? And it's cool. Okay, we see some people jumping onto that already. Someone's asking if they want if I could post my eight pages of mistakes. I'll see if I can find it. And I don't know if I can post it. It doesn't make any sense because it doesn't have the questions on it, so I don't know if you'd find it very helpful. It would be much more helpful if you made your own. People getting onto the live poll. Is the new syllabus HSC very different from the old syllabus past paper? You'll get plenty of electromag questions and your projectile motion questions and like energy. So like module 5 and 6 pretty much the same. There are some, if you look at like, I think they used to have like a space elective that will have some like module 7, module 8 questions. And I think those are still relevant. But yeah, you'll definitely, if you try one of them, there'll be a lot of like random content that I have to memorize that like we never covered. But yeah. Someone is asking some questions about Someone's asking a question about back to the double slit experiment. How do I know which minima or maxima is the first? So first is just everything's counted from the central point. So this is the central point, and then so the first one is like the one that's next, and like the second one. So like this, if we think about this as like 0, so that's the first one. This is also technically the first one because it's the first one from that central point. Yep. Okay, so I think all right. Okay, people doing well with the black body question. So yep. So let's just go through how we would solve it. So this is just a multiple choice question. If you pull up this equation. So as you can see here, you would because we want to find temperature. So what we want to do is we actually know we can figure out the peak wavelength. So the peak wavelength here is, if we kind of like look at it, that's around here. Estimate that's between the 400 and 600. I'm going to say that's 500 nanometers equals B on T. So then T would be equal to B on, and then we convert that to meters, so 500 times 10 to the negative 9 meters. So then that's 2.898 times 10 to the negative 3 meters times kelvins. And then that should give you about 5.9 times 10 to the 3 kelvins. I think last I remembered when I figured it out, it was a number that was like a little bit different, but it's closest to A, and so that's why the answer would be A. Yep. Okay. All right. Okay, so now the second one is the photoelectric effect. So, so before with ultraviolet catastrophe, we were like, okay, so we can only explain black body radiation curves if we assume that radiation is coming out as like packets of, in quantized packets. So then another problem that the light model couldn't really explain was the photoelectric effect. So the photoelectric effect, I'm going to really quickly go through what that means. So in this experimental setup, we have metal surface in a vacuum chamber, and then a detector. So then these aren't connected. So then light strikes the metal, and then what happens is electrons are then ejected from the surface of that metal, and then those electrons being ejected travel across the gap, where it kind of effectively closes the circuit, and then it detects that, and then it causes current to flow in this circuit. So what that tells us is when current flows, it's like, oh, electrons have somehow made their way from this metal surface to this detector, and it's basically due to the light striking the metal. Okay, so then scientists had a whole bunch, so expectation versus reality. The expectations of scientists for photoelectric effect, for what would affect the way that electrons would be emitted, was very different to what they actually found. So under the wave model of light, they would have expected that when we get light of greater intensity, the electrons being emitted would have higher energy. They also expected that when we expose the metal to the light for longer, the energy would build up in the electrons until enough for electron to escape. So if you just leave it exposed, light shining for longer, you would have more electrons being emitted. And they also they also predicted that, yep, the energy of emitted electrons would be dependent on the intensity of light. But what they actually found was that when they had light of greater intensity, it didn't affect the electron energy at all. It didn't affect like the kinetic energy of the individual electrons being emitted. What it did do was it increased the current, so it caused more electrons to be emitted. Because if we remember, what is current? Current is the movement of electrons. When we have more current, that just means we have more electrons moving. The second thing was that the emission of electrons was always instantaneous from the moment that light struck metal. If they shone light at the metal and it didn't, and nothing, no electrons jumped out, electrons were never going to jump out. But if it did, it was always instantaneous. And they found that instead of the energy of the emitted electrons being dependent on the intensity of light, they found that it was dependent on the frequency of light. So I would really recommend, this is like the summary of what you have to know and be able to explain in an HSC question. So I'm going to explain the observations that they made, and we can find that those observations only can be explained if we assume that light exists as photons. Right? So, okay. So the light hits the metal as photons. So photons are little packets of energy, where the energy packet is dependent on light's frequency. So that calls us back to Planck's little hack, E equals hf, where the energy of a photon, of the little packets of light, are dependent on frequency. So we're saying those packets of light are hitting the metal. So then what happens is that, so let's have a photon with, let's say, energy E, right? And then we have the electron in the metal, right? We're going to say this electron is charge of negative, yeah? And then so once it hits it, what happens is the electron will absorb the energy from the photon. And then after it absorbs a certain amount of energy, it can be freed from the metal. So, I don't know, let's draw this electron getting excited. So then this allows the electron to break free from the metal once it's energetic enough. And then so the energy that's now left over, so the photon gave it a certain amount of energy to free it, and then the rest of energy the electron carries as kinetic energy. So the kinetic energy then is dependent on the energy of the photon it absorbs and the amount of energy it takes to break the electron free. Right, so energy of photon energy absorbed by electron and then the remaining energy as kinetic energy. Right. And then so we call the Greek letter phi is the work function of the metal. So that's the amount of energy that the electron needs to absorb in order to break free. So this is phi. Call that the work function. So what we call the threshold frequency as well is the minimum frequency required to overcome the work function. So in this equation, E K equals HF. So that so this is the energy of photon hitting the metal, right? Yeah, and then so that's dependent on the frequency of the light. So that's frequency of light. So for example, if I've got, so let's say like the work function is like, I don't know, 3.9 times 10 to the negative 18 joules. Remember energy is in joules. If I had a photon with, let's say 2.9 times 10 to the negative 18 joules of energy, then the emitted, let's say 4.9 electrons would have, so 4.9 times 10 to the negative 18 minus 3.9 times 10 to the negative 18, which equals 1.0 times 10 to the negative 18 joules of energy, joules of kinetic energy. Okay, so let's do a Slido question. Oh well, a lot of people have already gone on to it. Actually, yeah. So, yeah, in this question, a beam of monochromatic light strikes a piece of aluminium in a vacuum chamber, same diagram as below. What does the frequency of this light need to be so that current will flow in the circuit? And then here we know that the work function of aluminium is 6.54 times 10 to the negative 19 joules. Okay, I'm gonna try and see if there's any questions. Someone asked, do we need to remember Wien's constant? No, it's on your formula sheet, as is the formula for this as well. Oh, someone asked for the photoelectric effect. Oh, really good question. Isn't intensity of light the same as the frequency of light? No, actually. So the frequency of light is sort of, if you can think about frequency, what does frequency mean? Frequency means how often something happens. So like this would be a high frequency of light. A high frequency wave would be, it's like troughs and peaks would be happening very often, versus like a lower frequency, like this. Whereas intensity talks about more about like how much light you've got. So if you're like shooting like brighter light at it, that would be something of higher intensity. So in the case of in the photon model, greater intensity light would be having more photons strike the metal. Someone asked if the speed of light is constant, then why does its speed change when traveling in different mediums? Speed of light is constant in a vacuum. Speed of light is constant in your particular medium. So speed of light is always 3 times 10 to the 8 meters per second in a vacuum. There is another constant speed of light depending on what you're in. So like light has a particular speed in glass. So light in glass will always have that particular speed. Isn't phi also the symbol for magnetic flux? Yeah, good question. Yeah, good point. Yeah, it is. Yeah. I think, yeah, it just becomes obvious based on the context. Like, stuff like this never mixes with magnetic field stuff. So, you will see that when you given phi in terms of in a photoelectric question, you're like, oh, that's work function. If you're given phi in a like a electricity or like magnetism question, then it would make sense that phi means flux. Okay, all right, really awesome. I'm just gonna put a pause on the poll for now. I think that people have gotten to have finished it. So okay, so the way that you do this is so KE is equal to HF minus work function, but we need the minimum frequency of the light so that this would be non-negative basically, so that current will flow, so that electrons actually get emitted, so that it matches the work function. So then what we actually need to do is when the energy of the photons is actually equal to the work function. So then because we're solving for frequency, we go work function on H. And then so now it's just a matter of subbing in is equal to 6.54 times 10 to the negative 19 joules over Planck's constant. This is in your formula sheet from memory, 6.626 times 10 to the negative 34 joules seconds, which gives us the answer of like 9.87 times 10 to the 14 hertz. Yep, and that gives you answer B. All right. So we're actually not going to get to spectral analysis today. Definitely, I like put this in as like if we get time to it, we'll get to it. But this section it's a little bit weird to be placed here. Basically, it's about the fact that all black bodies and also and like stars will emit lots of so they emit radiation, but there's sections at which there's particular wavelengths of light which get absorbed, based on certain properties, based on the elements that are in those stars. And what we can do is we can like look at their absorption spectrum and then come to conclusions about properties of stars. This is something I don't know why it's in module 7. It like seems to fit module 8 way more. But yeah, so you can tell stuff about its composition, its velocity, because if it's moving away, it would be shifted. If it's moving towards us, it would be shifted as well because of the Doppler effect, infrared density. And there was a Slido question as well. I think people going ahead sort of answer it as well. But yeah, I'm not going to go into too much detail about this because just because it's something that it doesn't need to be explained as detailed as stuff like the photoelectric effect and black body radiation. It doesn't really have an effect on this is just sort of like a byproduct of something that we can use to interpret stuff about stars. Yeah. But yeah, I'm gonna just leave some time for questions. This is technically a break time. We've got 10 minutes of break, so come back at 3:35. But at the same time, I'll just be answering questions as well. Can you still get a band 5 or 6 if you did average in the first test and failed the second test? The HSC externals matters much more than you realize. So yeah, definitely, if you smash that, the HSC externals, if you smash trials as well, definitely. If you hustle between now and then, yeah, definitely module band 5 or 6 is possible. Someone asked, do you have some more info on UNSW and scholarships in general? Okay, so yeah, so I personally go to UNSW, so I guess I know the most on UNSW. UNSW, a lot of applications start coming out in August, so you still got about a bit of time, 4 months. Check their website. They should get a whole list of scholarships available. The co-op is the big one. That's, I think, it's like almost double your tuition of the scholarship that they give you, and you also get like internships and stuff along the way. But that's only available for like computer science, commerce, and a couple engineering degrees. Yeah, so definitely do your research. Not just UNSW, like UTS, UCID, Macquarie, UWS. They've all got like really good scholarships. So definitely, and usually around August is when the applications begin. So just be checking those and apply for like everything that you're eligible for. Even stuff if you're like not completely sure you're eligible for, just apply. Just shoot your shot. You'll never regret it. I have quite a few questions asking about online resources and like what textbooks I used. I'll answer those like in the next like study break thing. Someone says apparently in chemistry 20% of the marks is on year 11 content. Is that the same for physics? I wouldn't be able to give a number. There's not really any questions that specifically ask you on year 11 content. It's just assumed knowledge, basically. Someone asked what subjects did I do in the HSC and did I study for physics the most? So I was a bit of a STEM kid. I did 4-unit maths and then I dropped it after trials. I did 3 units of English. I think I probably spent the most amount of time on English just because it was the toughest one for me. And I also like studying for English can be a rabbit hole. You can just keep reading. I did chemistry, I did physics, I did science extension as well. I studied for physics close to the most, I think. I think after English I spent the most time on physics. And then science extension also took up a lot of time. But basically, I don't know. Like the amount I studied was how much I liked it. Like I really liked English and physics, so I spent a lot of time on it. Chemistry, I didn't really care that much about, so I spent less time on it. Uh, is the trials more important or the actual HSC exam? If so, how much more important? Well, like you see the weightings, right? Like it's 50% of your mark comes from your HSC exam, and then 50% come from your assessments, and then trials is like a big chunk of your assessments. So like trials, in terms of weighting towards your mark, have like less of an effect than it used to because the trials aren't weighted that much anymore. It's only about like 30%, I think, 30 or 40, 30%, yeah. But what it is really good for is that it is kind of like a practice HSC exam. So it's really important in the sense that it's really good for showing you where you need to improve, pretty much. But yeah, like if you do crazy good in the HSC exam, it pulls you way up. Someone asked, does Module 7 provide the basis for Module 8? Yes. Uh, in the same way that Module 6 provides the basis for Module 7. Okay, so we have some more specific questions. Does the effect of acceleration or deceleration affect a point charge when it is self-propagating, and how does this affect the point charge if it is there? The point charge itself is like not the most important part when you're studying electromagnetic waves. It's sort of mainly just like, oh, so that's how a electromagnetic wave comes from. Yeah, like once it starts going, it kind of like just keeps going, like a particular wave itself. So I think what you're asking for, when like the acceleration, when the oscillation like frequency changes, what happens is it just like it produces another wave. The existing electromagnetic wave that has already been sort of like been going, it doesn't really have an effect. It's not like attached to anything anymore. It's just self-propagating. Again, like our model right now is like a gross oversimplification. Like a single point charge doesn't produce a single wave. It just like produces lots of waves, and in all directions. Is it true that whenever there is a magnetic field, there is magnetic flux? Yes. Yes, a magnetic field is basically magnetic flux. Like that's what it is. Okay, this is a good question. If light passed through, so this is back to like polarization. If light passed through a vertical polarizer and then passed through a second polarizer with a non-vertical slit, wouldn't the light be cancelled out? Okay. So the thing is, okay, so this is our like our plane polarized. And then this is like second analyzer. Actually, I'll probably draw it over it. So yeah, in a different direction. Someone asked like, why isn't the light completely cancelled out? Well, the thing is, this lets through only the components of light that are in this direction, right? Well, as you can see from here, if we look at this, actually this does have a if we break it down in terms of so if we sort of look at in terms of here, we can see that this actually has like a component of the light that is actually parallel. So we can think of this because we can think of any vector is made up of two perpendicular vectors, right? This is perpendicular. So there actually is, so this component is in the same direction as the analyzer. So what happens is that like that section of light actually makes it through. The thing is when it's like when it's perpendicular, it's like this doesn't have any component that's perpendicular to it, so that's why it cancels out when it's at 90 degrees. But when it's at an angle, there is actually still a component of the electromagnetic wave that is in the right direction. Really good question though. Back to the just to clarify, Malice's law is only for already polarized light? Yes. For light that has already been passed through like a first polarizer. So minima can be in terms of dark spot or bright spot, or is it only in terms in dark spot? So minima is the dark spot. Maxima is the bright spot. Yeah, so that's just terminology there. Do we need to remember Snell's law from year 11? Since it talks to different mediums and the speed of light. I don't. I did, because I was very paranoid that it would come up in the exam. It didn't. So yeah, I don't write the HSC questions, so I would say like better to be safe than sorry. And since Snell's law is still like very relevant to light, it could potentially get pulled in. So yeah, I'd say like you should know Snell's law. And then so again with Malice's law, if the light is going in all, it's not Malice's law, but polarization. If the light is going in all different directions before the first polarization, why is half in a vertical direction? Aren't they all in different directions? Yeah, they are all in different directions, but so that same thing about if we break them all down into like vertical and horizontal components, we'll find that, so like if we've got an analyzer here, and we've got, let's say like light maybe in like this direction, it does have a component that would still make it, and then so it's sort of like it's an approximation that about like 50% would, because it can either have the horizontal or vertical components. So like when you average it out, when it's all in all directions, about 50% of, if you divided them all up into vertical and horizontal components, you'd get about 50% horizontal component, 50% vertical component. How well do you need to know the pracs in the exam? Well, the thing is, if you know the pracs well, you understand the concepts well. So you should know the pracs really well. Is there an opposite polarization so you can increase the intensity of light? Oh, good question. I don't think so. Other than just like having more light. Yeah, I don't think, not in the syllabus at least. Yeah, we only talk about it decreasing. Someone asked back to the d sine theta equals m lambda. Like if you had to find this, what you do is you would usually like know this, this, and this. So then you would rearrange and then find d. Okay, also another really good question. Will the threshold frequency allow the current to flow in the circuit, or will it just liberate electrons because K equals 0, and they can't make it to the other side? Yeah, I know. That's a really good point. Because yeah, like K would equal 0, so like it's in this weird limbo state. Because we think of it as threshold frequency as a minimum. So like it has to be at least that frequency. So yeah, when it's at that frequency, nothing will be emitted. But even when it's like a tiny bit greater, yeah, the electrons will have kinetic energy. So when it says minimum, it just says it has to be like, think about it rather than less than or equal to. Think about it as a greater than or equal to. Think about it as like a greater than. It needs to be greater than that threshold frequency. Oh, okay. For the question I just demonstrated, would it be possible to explain how I get from the first line to the second? How did K disappear? Okay. I think this would be my last question before I get started with the next section. So I had KE equals HF. So this is a step of where, so we wanted to find the threshold frequency. Which is the minimum possible. So the minimum possible is where, so at the like point where, so before it overcomes the work function, this would give you like a negative kinetic energy. So when it's negative kinetic energy, that means the electrons won't be freed. But once Ke is greater than 0, that means electrons are freed. Yeah, so what you do is you find the point. We need to make, so to find threshold frequency, we need to make Ke equals 0. So then we have 0 equals HF minus that, and then which leads us to HF equals that. Yeah, so the reason the K disappeared was because we needed to make it 0 in order to find the threshold frequency. Okay, when you apply for scholarships, do you have to put certain degrees as your first option? Ooh, good question. I don't know. Because I thought, yeah, so when I applied for my computer science scholarship, I was like, I'm going to put computer science as my first one. But like, I don't have any idea if it actually affected the way that they looked at it. Well, actually, I do have friends who put it as like second choice and still got it. So, again, this is like a speculation game. I have no idea. Oh, this is a really good point. Does light diffract when passing through a polarizer because aren't they essentially tiny slits? My answer to that would be so light isn't diffract. So diffraction of light happens when the so if we think back to year 11 content, diffraction of light happens when the wavelength is greater um than the size of the slits. So actually, if your slits were like wider, then the waves would actually be able to pass straight through without diffracting. So that's my hypothesis, that in a polarizing, the slits are actually like much wider, so that light can actually just go through. When light is reflected from a pond as glare, why is it polarized? Why is it that it can cut out all the glare? Oh, because when it's reflecting from a pond, it's not polarized, like it's in all directions. So then when you put a polarizer on it, it cuts out light from like a lot of like the scattered directions, so you only get from a particular direction. So yeah, glare is like reflected light that's been scattered. And then once you polarize it, you put it back all into one direction, so that cuts out the glare. Would it be possible to remove all the electron from the metal, and would the metal stay without electrons? Yes. No, no. There's way too many electrons in the metal. And also if you look at this, right, the electrons go to this end and then they make their way back. So it's kind of the electrons are always being replaced. So no, you won't. So yeah, you'll never like remove all the electrons. But yeah, also like the metal can exist without electrons though. So that would be fine. Like the metal would still be there. It's just the electrons are gone. All right. Okay. So before we get into special rel, we also talking about. So a lot of people are asking about what books to use. So that's really awesome that TuteSmart actually has a bunch of books. And I don't think I knew about Unlimited. I used to have the physical books, but what we actually have is this thing where I'll show you the website. Yeah, so Ed Unlimited, it's like I think it's a subscription service, where you can get access to every single ATAR Notes, title. So, I think, yeah. So if you want to get into UCAT, or if you want to learn about biology, or you want to learn about chemistry, so here it's like a one-stop shop for like all of your different subjects. I think I'm previewing the one for the Victorian one. Oh, actually, let's switch to HSC titles. Yeah, you can look at the HSC titles. So yeah, let's look at where's the physics one? You can like search, I believe. Let's look at the year 12 physics notes. View now, 7 days free. Oh wow, I have to log in. Okay. Cool. All right. Yeah. So if you come to TuteSmart classes, you automatically get access to these. Yeah. So read now. There's some like really cool features. So you can like search for stuff. So let's search for like light. Right. Oh, okay. Wait. Let's do special relativity, because that's what we'll be starting off with soon. Yeah, yeah, you can skip to special rel, and there's the explanation for special rel. You can also annotate, you can highlight stuff, you can write, draw, yeah, and so it's really good. It's just having one place with like a lot of your notes. You can make study notes here, you can add a study note. Special rel is hard. Yeah, and then you've got like a little sticky note. Oops. You got a little sticky note there, and then you can open it to come back to later. So yeah, this is really handy. And I think, oh, okay, my unique code isn't there, but I can type it in. So the offer I think right now is for 14 days free trial, but I have a special code that is actually, how do I insert text box? It's Ngenie HSC. Shape format, shape fill. Like red. Oh god, that's a bit ugly. But yeah, it gets the point across. White. Yeah, so if you go use my code, you can get a 28-day free trial. But then also if you want the physical copies, which is what I had when I was studying, yeah, so like I went to like ATAR Notes lectures when I was in year 12, and I had these books to help me out. And yeah, if you use the code April HSC 15, yeah, you'll also get 15% off when you buy those books, and it'll get shipped out right to you. So really quickly, I think it's better off. I had like stuff prepared, so hopefully this answers a lot of the questions that some people were having about how to study. So like science of physics is all about understanding, especially with this new syllabus. So you can sort of split up your studying into like the calculations, the regurgitations, and the explanations. So calculations would be your formulas. So like as you learn your formulas on your formula sheet, what would be really good is just practice deriving them. And then in the process of deriving them, it makes sure that you've really solidified your understanding of why they exist. And then practice those calculations as well. Regurgitation, so this is just like syllabus dot points. So this would be stuff like Maxwell's contributions. Like it tells you exactly what you need to know there. So it would just be a bit of memorization. I actually would recommend spending less time on this because it's much better to spend more time on this. So explanations. So a lot of people are asking about what's the best way to study, create notes. I think the best way to study was to go through the syllabus, check if you could teach that dot point to someone, and then if you can't, figure out how. So it would be watching videos. There's lots of videos out there that explain in depth so you get like a better, broader understanding. Yeah, try teaching people, going through your pracs. And yeah, making notes is a really good way as well of solidifying understanding. For me, making notes was just also just a sense of like making sure I haven't missed anything from the syllabus. Yeah. So a lot of people ask how often did I study? I think in the previous thing I admitted that I'm a terrible procrastinator. So I studied for physics pretty like intermittently. Yeah, I don't work well on a timetable, so I wouldn't have like had a schedule of like every single week. So like if one week I was learning like a more difficult topic, then yeah, I would just spend more time trying to understand it. So yeah, so how often you study for physics is just when you're learning something in class where you're like, I don't know what's going on. That's your cue to study, and then study until you understand it. Yeah. And then someone's asking when I would recommend to start past papers. Once you think you've got, that's a good question. I think because now you don't have a lot of past papers and you're sort of like picking and choosing questions from past papers anyways, you would end up doing, it's more of sort of like taking questions from past papers as you go. And so I think it would be best to, I think trial papers, like if you can get past trial papers, that would be like studying for trials. But before that, you're just like doing, taking questions. Okay. Yeah. So just practice as much as you can, basically, with learning all the, with learning your calculations, being able to explain things. Okay, I'm probably gonna run at least 5 to 10 minutes over time, just warning, but I'll just cover special roll because I think, yeah, disclaimer, this is like a weird mind-bending concept, but it's very interesting. So special rel is based on two postulates. So Einstein said, so what a postulate means is just say, let's consider these statements as something universal, and then let's see what we can conclude building off of that. So first he postulated the speed of light is an absolute constant and the same in all reference frames. I think I addressed it a little bit earlier. When I say absolute constant, it's a bit of quotation marks. It's an absolute constant in a vacuum. It would be a different constant in different materials. And the second one was that all inertial frames of reference are equivalent. So let's break that down a little bit. So yeah, again, the speed of light is an absolute constant was something that they'd already sort of started to expect as scientists were measuring the speed of light. And then so we take speed of light to be c, which is equal to 3 times 10 to the 8 meters per second. I think it's on your formula sheet, but definitely this value, memorize, know it off by heart. But the cool one is that all inertial frames of reference are equivalent. Okay, so let's break that down. What does inertial mean? Inertial means non-accelerating, so an object that might be at rest or traveling at constant velocity. So that could be like if I'm driving in a car on a highway and you're maintaining a speed of 100 kilometers per hour, you would be in an inertial frame of reference. So what that also means is that the idea that everything is relative to one another. I am only able to see that I am moving because I can see that other things are still. So if you're on a train, traveling at constant speed, how do you know that you're moving? Well, it's because I can look outside the window and see stuff moving past. And then so that's how I know I'm moving. But what if that window was closed? What if that window was closed? We're traveling at completely constant velocity, so like there's no bumps or anything. The answer is we wouldn't know that we're moving. Because in our frame of reference, everything is behaving as if it was stationary. So this is like how we're able to be on Earth, right? And we're spinning at like, I don't know the speed, but like our Earth is orbiting. Our Earth is 1 orbiting, 2 spinning on an axis, but to us it seems that we're at rest. It's because from our frame of reference, everything that we see is at rest. So we think, so yeah, our movement is not relative to the movement of Earth. Our movement is relative to everything else. Everything else is moving with us. So it appears that everything else is at rest. Yeah, and within an inertial frame of reference, all of Newton's laws hold up. Okay, I'm getting a couple questions of science extension. I will come back to that later. Okay, so yeah, now back into the special rel explanation. So why were those two postulates such a big deal? Okay, so let's think about the train thought experiment again. So I'm on a train and it's traveling at a particular velocity, right? Okay, so we have this device called a light clock. So a light clock is it measures, so it's a beam of light going from a source to a mirror, bouncing back, and then sensor. And so one tick is the time taken for a beam of light to bounce back. So we're gonna pretend that at the ceiling we have a source of light, and it's yeah. So with our light clock, it's just bouncing from this floor to the ceiling. All right. Well now, so if I'm inside the train, I see that light bouncing up and down. That's what we should expect when because to us this train, we're moving at the same velocity as the train is at rest to us, so it just moves up and down. And also if we were at rest and looking at the train, we would see it just move up and down. But something weird happens when we're traveling at close to the speed of light. So as you can see in here, if we're observing from outside the train and we're so pretend this is like a transparent train, we can see that as in the time it takes for the light to reach the floor, the train has moved, and then so it actually has to travel a diagonal path, and then so once the and then so after another so once it bounces back up, the train has moved again. So what we can see is that instead of the light traveling straight up and down, so stationary, so in a stationary point of view, the light travels down and up. But when it is moving, I should write it here. It travels this way and then up this way. So that's going to be a greater distance than this. And so since the distance traveled by the light is greater, but postulate 1 tells us that the speed of light is an absolute constant, that means a longer time has been taken for the light to move down and up. So if the stationary observer sees a time of t0, let's say t0, that's the amount of time measured to go up and down. From our perspective of looking at the light in a moving train, and we see t, we would conclude that our measured time from outside the train would be greater than the time measured inside the train, or if the train was stationary relative to us. So yeah, that's the big concept, time dilation, that time passes more slowly for fast moving reference frames. So the important distinction to always make is that t0 is proper time. So proper time is the time in the reference frame at rest relative to the light clock. So in this example would be if you were standing within the train and the train was going, if you're standing within the train, your reference frame is at rest relative to that train. And then so, yeah, your time that you measure is t0, also known as proper time. But then t is that when you're measuring the light clock which is moving, you're an outside observer, and that's t. And then so it's given in that equation which is on your formula sheet. Then velocity v is the velocity of the moving frame relative to your observer. And then so Yeah, so then you end up with t being greater than t0. And then likewise, I'm not going to go into the derivation for this, although I recommend reading more about it if you can. Length contraction also happens. So length contraction is when the length is measured to be shorter for fast-moving reference frames. So same idea, where proper length is the length in the reference frame at rest relative to the object. Your measured length is measured by observer, and v would be the velocity of that moving reference frame relative to the observer. And yeah, so L equals, yeah, so for this one, with length contraction, then L is less than proper. So at relativistic speeds, time appears to be longer, but distance and lengths appear to be shorter. Okay, so once that sinks in, let that sink in. The hardest part of these questions is actually just define, because once you like understand it, most of the questions are just about plugging in the numbers to the formula. So then the hard part is knowing which one is proper time and which one is the relativistic quantity and which is the rest quantity. Yeah, so in an example, so if I'm measuring the length of a spaceship moving at 0.2 c, so 0.2 c means 0.2 of the speed of light, my reference frame is relativistic because the spaceship is moving with respect to me. The length of the spaceship at rest would be L0, and then my measured quantity as the spaceship is moving would be L. But if you're inside that spaceship, there is no relative motion because you're traveling at the same speed as that spaceship. So that spaceship is at rest relative to you. And then so you would be measuring the rest quantity in there. So special rel was really wild because it basically tells you that time and distance are different for different observers. So at the time, people were like, what the heck? But then it's actually been proved with experiments that you'll learn about in your syllabus. So you'll learn about the muons, the atomic clock experiments, about particle accelerators. I'm going to just go through the muon thing, and hopefully that helps a little bit with like understanding as well. So first of all, muon decay. Muons are tiny particles produced in space. So they're produced about 10 kilometers above the Earth. They decay in about 2.2 nanoseconds. So they're produced, and then in 2.2 nanoseconds, they die. Of course, this is an average decay. Some will last longer, some will last shorter. And they also travel at about 0.98 c. Actually, if you look online, there's a couple of different figures for their speed of travel. I'm just going to go with 0.98 c just for calculation purposes. So if we think about it in non-relativistic circumstances, if we just think about it in the distance it travels, using the formula speed equals distance on time. So if we think about like speed equals distance on time, right? And we know the muon travels at 0.98 times 3 times 10 to the 8 meters per second. And we know that it decays in 2.2 times 10 to the negative 6 seconds. We figure out that on average, it would travel about 646.8 meters before decaying completely, which is pretty impressive. Like it lasts for like 2.2 nanoseconds and it gets 650 meters through the air. But this is still far, far away from Earth, which is still like almost 10 kilometers away. So you would expect that very few muons, maybe like a couple muons that happen to have a crazy long lifespan, would make it to Earth's surface. But scientists actually did find a lot more muons than they would have expected to Earth's surface. And then so the amount of muons that they did find actually aligns with the amount of muons that would be predicted if you took into account special relativity. Okay, so let's think about this in terms of special rel. So from the perspective of a muon, so we have a muon here, and this is like Earth, right? So muon has to travel a certain distance. Let's call that a certain distance to Earth, right? So we want to see what is the distance that the muon sees. Because it's traveling this fast, what is the distance it perceives that it is away from Earth? So for this, we need the equation L equals L0 1 minus V squared on C squared, right? So yeah, we have the number that the muons are 10 kilometers above the Earth. So 10 kilometers, we need to ask ourselves from which reference frame? Well, it is from our reference frame. It's from our reference where we are we're at rest relative to the Earth. We measure that the distance between the muon and Earth is 10 where the muons are produced, and the Earth is 10 kilometers. So that's the proper length. That's the proper distance. So L0 is equal to 10 kilometers, right? And then so distance seen by Earth whereas L, which has been length contracted, is the distance seen by muon. Right? And then V would be the velocity of muon. So then if we sub that in to find the distance seen by muon, so that's 10 to the 4 meters, 1 minus, what's the velocity of the muon? 0.98 c squared on c squared. And then if we simplify that, put in your calculator, so the c squared's cancelled, so you end up with 10 to the 4 over 1 minus 0.98 squared, which gives you, which should give you, I think I wrote down the answer down here. Which should give you 2 times 10 to the 3 meters, which is about 2 kilometers. Yeah? So what that means is, although we from Earth seem to think that the muons have traveled 10 kilometers to get to Earth, the muon thinks that it's traveled 2 kilometers to get to Earth. So then in that time, then a lot, so to travel, so since, so with that 2 kilometers, in the time it takes to, more muons would be able to make 2 kilometers versus making 10 kilometers. So you would have some muons actually reach Earth that the scientists ended up detecting. So now I want to do muon decay for So now let's think about it in terms of time. So that was from the perspective of the muon. Now let's think about it from the perspective of an observer on Earth. For the observer on Earth, it would appear that so remember how time moves more slowly for moving objects? Well, so yeah, the time that that's measured for the lifetime of the muon is actually going to be longer from Earth's perspective. So when we say that the average decay is 2.2 nanoseconds for a muon, that's the same. That's if we're in the same frame as a same rest frame as as a muon. If so, from the perspective of a muon, its average decay is 2.2 times 2.2 nanoseconds. If we had like a still muon next to us, its average decay would be 2.2 nanoseconds. So T0 would be equal to so decay time in same reference frame as muon. But since from the perspective of the Earth, the muon is moving, it's going to have a different. We're going to observe a different decay time, right? So we have T equals T0 on 1 minus V squared on C squared. So this is the decay time at rest, and then this is decay time of moving muon. Alright, and then so we can sub that in. So that's equals to 2.2 times 10 to the negative 6 on 1 minus 0.98 c. So again, the same velocity of the muon. There we go. And again, the c squareds cancel. Right. And then if we plug that in, that will give you 1.1 times 10 to the negative 5 seconds. Right? So yeah, that's actually quite a big difference. That's a so a muon has a lifetime of 2.2 times 10 to the negative 6 seconds. But from our perspective, the moving muon has a lifetime of 1.1 times 10 to the negative 5 seconds. So from our perspective, it seems that a muon is able to live longer. And so that's why more of them are able to reach the Earth. Okay, so that was pretty intense. It's okay if that seems like a lot, because it kind of is. It is a lot. This is a very tough concept, but I want you to have a go at this question. So a next-gen spacecraft developed by NASA has a rest length of 50 meters. This craft can reach speeds of 0.2 c, so that means 0.2 of the speed of light. What would be its length while traveling at this speed, as measured by someone back on Earth versus someone on the craft? Okay, there's quite a few questions coming in. I'm just going to try and answer them while we're doing the polls. Okay, really good point. For time dilation formula, what's going to happen when v squared is greater than c squared? So then wouldn't we get an imaginary value? Really good point. So that's mathematically impossible, and then it's also physically impossible. So c is actually the speed limit of everything. Nothing can travel faster than the speed of light, and that's just like that's a consequence of special rel. So yeah, you won't ever find anything that's traveling faster than the speed of light, and that has to do with like relativistic momentum. Someone asked, okay, yeah, a more accurate value would be 2.99792, but yeah, and for our calculations, 3 times 10 to the 8 meters per second will do. About photoelectric effect, you always need a circuit to remove electrons from metal via photoelectric effect. No, you don't. If you shine light at any metal, you will get electrons coming off of it. Just the way that we use a circuit, because that's the only way that we can detect the electrons coming out. Yeah, because otherwise we wouldn't be able to detect the electrons. What does it mean by fast moving reference frame? So it's just something that's moving like really fast, as in like close to the speed of light. So 0.2 c is like pretty fast. Yeah, so it's just a reference frame is just anything that you can like observe from. Oh, okay. Well, really interesting point. Is Earth an inertial frame of reference even though it orbits the sun with some centripetal acceleration? Yeah, it's still an inertial frame of reference because we traveled at the same speed. I should have clarified. So it's when we're maintaining the same speed. Yeah, because if you can see from the equation, like when you square it, it doesn't really matter what direction the velocity is in. So yeah, our tangential velocity is always the same. Our tangential speed is always the same. So yeah, we are an inertial frame of reference. Does special relativity mean that in relative motion we have to take into account time dilations and length shortening and make year 11 relative motion invalid? Yeah, because in special rel, okay, year 11 relative motion is valid when we're kind of moving at like normal speeds, so like up to like only when you're like moving at like half the speed of light does relative motion start to actually screw with things. So in year 11 we only really cared about stuff that was happening on Earth. So stuff that's happening on Earth, nothing's ever going to move fast enough for relative motion to have a massive effect. But yeah, if we're doing like super fast stuff, we do have to take into account time dilations and length shortening. However, you're not ever going to be asked for like a super complicated question that asks about like relative motion in terms of like by accounting for time dilation. Yeah, hope that helps. Someone asked about the aether wind impact the light to the same extent regardless of rotation. If you actually, I didn't get to do as much into depth about stuff like measuring the speed of light as I would have liked. But when they did that experiment, they actually found that the ether didn't exist. So yeah, so they used to think that light moved in a medium, but yeah, now they found that no, light is the constant, and there is no ether wind. Oh, someone asked if Earth is orbiting and spinning on its axis, shouldn't the distance to the muon sees be greater, not less? Okay, well, think of it like this way. The muon gets to the Earth uh, in like within nanoseconds. How much does Earth move within a nanosecond? Not very much. So the sideways movement of the Earth doesn't actually have. We can assume that the Earth is not orbiting in this direction in this case because yeah, considering like the Earth doesn't move much sideways in the time it takes for the muon to get here. Okay, so I'm gonna look at the poll and wrap up. So yeah, okay. So for that first question, the length while traveling at this speed measured by someone back on Earth. So in this case, the craft is traveling relative to us. So we do have to take into account length contraction. And then so what you would do is you would go L equals L0, 1 minus v squared on c squared. And then so L0 would be the length of spacecraft at rest. Which would be equal to 50 meters. And then, so this is 0.2c. And when you sub that in, yeah, you get about 49 meters. And that's the length measured by someone back on Earth. And then next question, someone on the craft. So for someone on the craft, they are actually at rest relative to the craft. So they measure its rest length, which is 50 meters. All right. Okay. So that's about all we have time for today. I'm about 10 minutes over time. Some people have gone to this question. Anyways, the answer is B. I'm going to write up fully worked solutions. I have fully worked solutions that will get sent to you next week, which will explain how that works. But yeah, so I got through like the main bulk of what special rel is. Definitely, it's a tricky concept. I recommend watching lots of YouTube videos about it. So there's this really cool video. I'm not going to follow it now, but if you search up simple relativity, the first video that comes up explains it really well. And you just need to go through the thought experiments in your head and solidify that. Have a go at deriving time dilation and length contraction. And yeah, just like let it sit in your head and then come back to it and see if it still makes sense. But yeah, that's kind of all we have time for today. I am still going to be, so that's it for the content part, definitely. Thank you so much for making it today. I'm definitely still going to be answering questions from the that you're still sending through, just about studying and the content so far. But yeah, so today we went through most of module 7. Actually, we talked about light, we talked about electromagnetic waves, we talked about we had a look at the wave model of light, and then we sort of looked at and we kind of proved that light behaves as a wave. And then we saw there's some instances where no, light seems to behave as a particle. And then so that wave particle duality gets resolved definitely more in module 8. It will start to make more sense. Right now we're just like, it's both a light, it's both a wave and a particle. And then so like right now it's kept to those pracs, so just understand those pracs. And then we got to look at special rel, which we don't do pracs for that, it's all thought experiments. And yeah, so like just remember the two postulates, that the speed of light is an absolute constant in a vacuum, and that all frames of reference are equivalent. Okay, all right. So let's go through some questions that you guys have. Um, yep. So online resources. There is. So obviously the ATAR Notes stuff is really good. Um, there are. Oh, what was it called? There's a YouTube channel that's really good. I think it's called like High School Physics Explained. Saved my life. Amazing. Watch those videos. Um, yeah, I think USID also publishes some stuff uh to do with yeah, USID publishes some documents. But I don't know if they're all super accurate, but yeah, you can find that. Yeah. How do I manage my time well while writing answer for questions in the exams? Um, I think a really good way of doing it is that when you're making an answer, address all the really obvious things first. So just go like define the keywords and write down a formula. And then from there, you go look, oh yeah, how much time do I have? Um, and then just like, and then once you get to like, you haven't like quite finished the answer, but you see that you're running out of time, well, you've already like gotten like 1 or 2 solid marks just from like defining the concept. So so then you're a little bit more comfortable with like moving on and like trying to address another question. But yeah, I think there's like a point per mark allocation. I don't recall off the top of my head. But yeah, figure out it's like add up the total marks and then divide it by the time it takes, like the 3 hours you've got. And then that should be a guideline on how much time you should be spending per mark. Um, Making study notes for advanced mechanics or electromag. How do you go about it? Definitely syllabus open next to you. Your school textbook or like an ATAR Notes book or like any textbook also as references, and then go through the syllabus dot points and then um, look at the online resources and then summarize them. Um, yeah, that's how you make study notes for any subject, I guess. Uh, for both advanced mechanics and electromagnetism, I would recommend lots of diagrams should go with those notes. Um, so ask which notes are more efficient, electronic or written. For me, it would have been written because back in year 12, because in physics, it would have been a lot of drawing diagrams. Um, actually, I used both electronic and written. So for module 5 and 6, because it needed diagrams, I used written notes. For module 7 and 8, which was more like concept, I use electronic notes because it's like more efficient to type. Whatever works for you. If I'm saying things and you like disagree, like go for your life. Like it does, like how you make your notes should be in the way that's best for you, that you feel helps you remember things. Specific tips for student learning physics over Zoom with the teacher in a different city. Oh, okay. Yeah, I know. Yeah, like even at uni, like learning over Zoom, it's harder. Um, I would say try using that chat feature. Um, like don't be afraid to shoot questions over. Um, I think to help with interactivity, like I know some people like they work on a Google Doc together. There's like interactive whiteboard apps out there that you can use to like draw at the same time. Um, but yeah, I think that also means you're gonna have to like supplement it a lot with like watching YouTube videos in your own time as well. But definitely like yeah, like don't be afraid to like email your teacher at any time. Um, Someone asked about how would you answer short repose questions. Um, yeah, so like when I did that electromagnetic wave question, I definitely I looked at the key verbs, the key terms, Um, the key terms of the syllabus, I don't necessarily think about, because the syllabus is sort of like your knowledge is the syllabus anyway. So I definitely, yeah, the key verb. But I think the mark allocation tells you like um, how much you like need to write. So uh, I'll go off this special rel question. So outline a thought experiment that relates to the prediction of time dilation. So outline, it just means sort of like a brief overview. 3 marks also tells you don't have to go super in detail. I definitely also recommend drawing a diagram whenever you can to short response questions. So yeah, your approach should just be, yeah, look at the key verb, look at like the key words, so like thought experiment, time dilation, and then also the linking word is really important, so like relate. So be really sure to like talk about the thought experiment, talk about time dilation, and then show how they linked. And I think the linking part is where a lot of separates like the people who are just regurgitating the syllabus versus the people who understand what they're talking about. Okay, I'm gonna do a couple science extension questions. Science extension is what you make of it. I did science extension because I wanted to do a research project. And I also ended up finding the philosophy of science stuff really interesting. I would say definitely like don't think of the philosophy of science stuff as like a chore. Definitely try and like appreciate it and that sort of and like understand it. Science extension is, yeah, it's an interesting subject. Do it, yeah, like do it if you like love science and want to just like know more about it. Um, Also, the other tip is time management. Make sure you're plan your, so like make a deadline to get your experiment done, and then aim to get it done like 3 weeks before that. That's my top tip for science extension. If you failed year 11, should you revise over that content for year 12? Does it matter a lot? Yeah, you should revise over that content for year 12. Definitely I think more in terms of if you're studying year 12 and there's like a concept that you don't understand that came from year 11, revise that. Yeah, I think that would be my hint for that. Because year 11 is more important as like a building block for year 12. For understand, like it's like the prerequisite knowledge you need to like understand year 12 properly. Let me see if do you have to understand Hertz's experiment for production of electromagnetic waves? I would recommend reading about it, but I don't think it's something that you get. I recommend reading about it, but it's not like it shouldn't be your top priority to be able to explain it. Is it worthwhile to do all the past papers, even the one from the old curriculum? Is practicing past trials worthwhile as well? Like don't do the full papers because there's like I think about 50% of it is like no longer relevant. So definitely past paper questions are only useful for the questions that are still relevant to our current syllabus. What was a science extension exam like, and what extent do you need to know about statistics? You should definitely know about statistics in the sense that you need to know how to apply them. You need to know how to use them. You need to know when to use what type of statistical test. because yeah, because we did get most of the questions were about interpreting science media and like saying like the reliability or like talking about experiment design. But yeah, there was a question where you had to apply statistics and yeah, just knowing like what sort of data. I'd be able to identify the type of data and being able to know what type of statistical test to use for that. But yeah, good luck to the people who are doing science extension. Um, how many hours did I study a night? Did this increase, decrease your productivity? I I think I studied a lot. Because I also did like a lot of I used to like so after school I'd like usually have some sort of like extracurricular, and then I'd go to the library, and then I'd stay at the library until about 8 p.m. So that's probably about 3 to 4 hours of study a night. Um, it wasn't consistent though. Let me tell you that. Yeah, this was more closer to trial period. I was definitely studying like about 4 hours a night. Did this decrease my productivity? I was just trying to like get through stuff and understand things. Um, but yeah, like I've always been a big believer if like I feel that I'm too tired to like go on, like that's it for the night. So I study as much as I feel productive for. In my opinion, what is the hardest module and why? Um, Module 7, I think, because special rel's in it. Actually, electromagnetism was pretty hard as well. Module 6, I think getting my head around Module 6 was the hardest. Um, yeah, okay. So, I think, damn, there's like a lot of really good questions that I want to get through. But I'm just gonna maybe answer one last question about, just like about computer science, I guess. Um, Computer science at UNSW. Well, I've just started, but you basically have to do like it is pretty flexible, definitely. There's like the core subjects, but if you're interested in hardware, you can definitely there's plenty of electives, um, and you can also choose to take the electives that are more theoretical focused or like more practical focused. Um, And like, yeah, I'm studying computer science, but I never did like IPT or anything. I think maths is the most important subject that you're doing now that would be relevant to computer science. Um, yeah, okay, so yeah, unfortunately, I'm gonna have to wrap up that. Thanks for if you've been staying for the rest of I've gone a little bit over time, but yeah, thanks for hanging out and seeing all the questions. Um, yeah, so everything will be up on the slides, and up on the slides, I'll write up all the solutions, and they will be sent to you. So keep an eye out on your emails. But yeah, thanks for coming, and good luck for physics.